second session. And the first talk is going to be by Jack Harris from Yale University. Jack, what is yours?
Hi, everyone. Thank you. Can you hear me?
Yeah, we can hear you.
Okay, good. And do you see a full screen slide?
Now, yes.
Okay, good. So thanks to the organizers. Thanks for the invitation to be here or to join you. I've been enjoying the talks a great deal. And it's as someone for whom, macroscopic quantum phenomena is sort of appealing in part because the potential for making connection with questions about quantum gravity, it's fantastic to listen to all this knowledgeable people in one place at one time. Usually I feel like I'm often the only person in the room when I give a talk who's talking about this, and I'm not particularly well qualified to really explain the ideas, which I try to always make clear in my presentations. So I'm not going to say much really about quantum gravity or specific models or specific things that one might test, because I think it's been presented very thoroughly already in the talks this week. So I'm just going to tell you about some experiments that we do on optomechanical systems, where one of the motivations that we have for them is that they seem to provide a nice way of accessing quantum effects in surprisingly large objects. Whether or not that's in a way that ends up being useful for specific questions about gravity or space-time geometry, I guess, is an open question, and I would be interested to hear feedback on. I'll talk about optomechanical systems in which we use single photon detectors as a resource for nonlinearity at the single quantum scale. This is, I think, a pretty well-known story, but I'll go over it a little bit. I will talk about optomechanical systems that are built using superfluid helium, and that is a little unusual, so I will give a brief advertisement. I think superfluid helium is a vastly underexploited material for quantum optics and quantum acoustics. I'll talk about our specific results, which mostly focus on measuring phonon-phonon correlations in mechanical resonators, and then talk about sort of where we're headed next. And I want to mention that this is done in close collaboration with Jacob Reichel's group in Paris, with a number of theory colleagues who've helped us out, and of course, I'd like to acknowledge our funding sources and the students, and in particular, postdoc Yogesh Patil, who's led this project. Okay, so the first thing that I wanted to talk about is how photon counters can serve as a strong source of strong quantum nonlinearity for optomechanical systems. And the basic story is the following. If you have a perfectly rigid optical cavity and you send in green laser beam, the laser beam will come back green. On the other hand, if your optical cavity incorporates some kind of mechanical oscillator, here I've shown it as a movable end mirror, but that's not crucial that it be this way, then the oscillations of this object will impose phase modulation sidebands on the light. This is a completely classical effect. There's no reason to invoke quantum mechanics here. But if you were detecting that light click by click with a photon counter, then each photon that arrives here is certainly either an unshifted green photon or a blue photon or a red photon. And so with each click, you're entitled to ask, well, how did I start from just a bunch of green phonons and suddenly get a blue photon? And the answer is that in that case, the electromagnetic fields swapped a green photon for a blue photon by absorbing exactly one phonon of mechanical energy from the mechanical oscillator. And likewise, each red click corresponds to an instance in which the incident light deposited exactly one phonon in the mechanical oscillator. So these red clicks and blue clicks, if you can identify them as such, are serving to herald the addition of precisely one phonon in the mechanical oscillator, or the subtraction, depending on which color. That's a powerful resource because, if you like, this is a measurement whose back action serves as a nonlinear drive that is adding a known, or at least a heralded, number of quanta to this mechanical oscillator. In practice, this is difficult to implement because most of the single photon detectors that we have don't provide us with the information about the wavelength of the light that they absorbed, at least not if the frequencies are being shifted by an amount that's typical of mechanical oscillators. The environment is probably acquiring that information, but not the experimentalist. And so a challenge in implementing this kind of approach to realizing nonlinearities is just that the weakness of the optomechanical interaction is such that only a small fraction of the clicks carry interesting information, and just the usual single photon detectors themselves don't provide us with the information that we would like. So the basic idea in these experiments is just to use a very effective filter cavity. And this is really kind of a brute force approach, but the idea is to build a filter cavity here, which is such that when there's a click at this detector, you really know that it had to have been a redshifted photon. If you like, this cavity is restructuring the modes of the electromagnetic field such that the only modes that this detector has back action on is the redshifted one. And this kind of idea has been around and employed in traditional cavity QED systems for a long time. It has been applied to optomechanics, first in a proposal paper, and then used very successfully by the Delft and Vienna experimentalists. And all we want to do is to take this idea and implement it in our own optomechanical system. So our system is in some ways very conventional. It's just a Fabry-Perot cavity coupled to a mechanical oscillator. But there are a couple of unusual things about how it's built that it's worth describing here. One thing is that the more or less conventional Fabry-Perot cavity is realized between the end faces of two single-mode optical fibers. And that's sort of shown. These are actual photographs of the two mirrored fibers here. This is a technique that's been developed in Jacob Reichel's group and that he's generously shared with us. This is a cartoon of the stable optical mode confined between the two curved mirrors. And a nice feature, very nice feature for us, is that this optical mode is actually pretty well coupled to the traveling waves that run up the fibers. So the point being, once you take these fibers and find a nice way to align them, it's very rigid and compact and kinematic, and the whole thing is epoxied in place, what you have is a little chip of glass with two fibers running out that you can bolt to a dilution refrigerator. Those fibers run out of the fridge and plug into your fiber optical system. There's suddenly no input optics, no mode matching, no free space optics of any kind, and it becomes basically a chip-based high-finesse optical cavity. Just as an optical cavity, it's not particularly interesting to us, so to have some mechanical degrees of freedom, we simply fill it with superfluid helium. And superfluid helium is not the most common choice of material for quantum optics, but it really has some fantastic properties. If what you're looking for is a material with very low optical absorption, liquid helium has the largest band gap of any condensed matter, and much more importantly, it has typically 0 atomic defects in a macroscopic sample. So just no way for there to be any mid-gap states that could absorb near-infrared or visible light. If you're interested in very low mechanical loss, that absence of defects and the vanishing viscosity in the superfluid state is certainly potentially an advantage. From a practical point of view, it's one thing to make a beautiful device and bolt it to your refrigerator. It's another thing to ensure that the relevant modes of that device are actually cooled by the refrigerator. And here the fantastic thermal conductivity of superfluid helium is an advantage in this regard. In this particular design, the modes that we'll be interested in are the acoustic modes of the superfluid helium, which is conventional density waves, just like you would have in air or water. And they are confined by the same mirrors as the optical cavity. And while this has nothing directly to do with superfluid helium, having an optical cavity and an acoustic cavity that are defined by the exact same boundaries and obey essentially the exact same wave equation is a huge advantage. It means they're naturally self-aligned. They're naturally perfectly overlapping. So not only does the cavity construction remove any need for in situ alignment, the filling it with superfluid helium just gives you naturally aligned mechanical natural alignment between the mechanical and optical degrees of freedom. So while we love products like attocubes and the JPE cryogenic translation stages, it's also nice not to have to use them. Superfluid helium also has a lot of the other desirable features of materials in these fields. It can host interesting hybrid quantum systems. I won't say much about that. And superfluid helium has some interesting advantages as a target material for searching for low mass WIMPs and the like. I also won't say much about that. Because what we're interested in is just optomechanics, the idea that light stored in this optical cavity can be used to transduce, to measure the phonons in a certain acoustic mode. And the manner by which these two modes couple to each other is just the fact that liquid helium has index of refraction. And so when it becomes denser and less dense in the course of a sound wave, that index of refraction is modulated. And as long as the optical field overlaps with those density fluctuations, they will detune the cavity. Okay, this isn't the actual end mirror moving. The cavity's physical length isn't oscillating, but the cavity's optical length is oscillating. Its index of refraction is oscillating. And at the level of the Hamiltonian, that's the same thing as the cartoon that I showed you before. There's one more elegant thing about this construction that I'd like to mention, which is that in optomechanics, sort of persistent problem is that you have an optical cavity, it's very nice, you have a mechanical oscillator, it's some very nice object, but that object has an extremely large number of vibrational modes, and they all usually detune the cavity in some way. And so all those modes are being transduced when in fact, usually one has only carefully engineered or is only interested in one of those modes. But the fact that we have the situation in which the optical geometry and the acoustic geometry are identical means that there's a natural orthogonality relationship between the optical mode, I've shown the same optical mode over and over again here in red, and all of the different acoustic modes. I've shown the change in density in blue, such that if you take the overlap integral of this optical mode and this density wave, it's 0. The overlap integral here is 0, so there's no optomechanical coupling. Here it's 0, so there's no optomechanical coupling. Here the integral is maximal, so there is coupling. And then it's 0 again for every other acoustic mode. So the point of this is that once you send laser light into a specific optical mode of this cavity, it transduces one and only one acoustic mode. So this is a particularly nice way of getting at truly single mode optomechanical coupling. And if your laser wavelength is a nice telecom wavelength, you couple to the acoustic mode with exactly half that wavelength, which turns out, given the speed of sound in liquid helium, to be a 315 megahertz mode. And that's a reasonably convenient frequency for a lot of applications. A single device looks more or less like this, but they're sufficiently simple to make that we usually put a few of them together. They just go inside of a can that can be filled with liquid helium, and the can gets bolted to a dilution refrigerator. The only connections to the rest of the world is one fill line to fill up the entire family of devices, and then one optical fiber for each cavity. There's no electrical leads, there's no microwave coax, there's no piezos, there's nothing else. That's all that it is. And as a result, a conventional dilution refrigerator could easily accommodate hundreds of these devices. And at the very end of the talk, I'll discuss our plans to not just fill up a dilution refrigerator with lots of heterogeneous devices, but I'll describe a scheme by which I think it's feasible to make all of those devices indistinguishable at the quantum level. Okay, but for now, the actual measurements. The setup in cartoon schematic looks more or less like this. There's a laser that might be detuned to the red sideband of the optical cavity or to the blue sideband. We can switch between them. Light is sent into the cryostat where it interacts with this optomechanical device I've been telling you about. The light comes out with the boring unshifted photons, but also the interesting sideband photons. There's a series of cascaded filters that pass only one of the motional sidebands, and those go to superconducting nanowire single photon detectors. In a typical experiment, we might just choose one of these lasers, say the one detuned to the blue of the cavity. The point being that oscillations of the acoustic mode will produce sidebands on this laser tone, but only a certain sideband is resonant with the cold cavity and passes through the filter cavity. In the data, I should mention, so we go through sort of a series of locking up all these cavities and lasers and then letting it run freely and switch back and forth every 200 milliseconds. And during the 100 milliseconds where we're actually counting, taking data, the individual photon arrival events are extremely high signal to noise ratio with extremely good timing resolution. So each of these photon detections nominally corresponds to the addition or subtraction of exactly one phonon from this acoustic mode. if we measure the rate at which events like this are happening as we vary the detuning of this laser, what we see is, of course, there's a flat background, there's stray lights of various kind. There's a peak in the background counts, which we've identified with the thermal fluctuations of the room temperature optical fibers. This is just sort of always present. It's a phenomenon known as gauges. But then there's this peak at exactly the 315 megahertz frequency that's expected for the motional sidebands. And I should stress this line shape isn't the line shape of the mechanical oscillator at all. It's just what happens as we tune this laser frequency and so drag the sideband frequency along. And what we're seeing is the sweeping out of the filter cavities line shape. And that's what this is a fit to. So we go through various characterizations to check that these interpretations make sense, and indeed they do. We can also take the same kind of data by putting the laser over on the red side, in which case the data looks very similar backgrounds, similar gobs feature from the optical fibers, and again, a similar narrow peak associated with the phononic sidebands, but with a distinct difference in the height of these two features. And we can identify this as the quantum sideband asymmetry. Of course, that identification requires some care. Some of the kinds of characterizations that we go through is just to measure the heights of these peaks as a function of the temperature of this device. And if you do that, you see a few things. You see that as the device gets hotter, the rate of sideband photon production goes up. And it's nice and linear in the fridge temperature down to a temperature somewhere below 50 millikelvin. You can also see that this difference between the red and the blue sidebands is persistent across this entire temperature range. And this gives us confidence that this is indeed the quantum sideband asymmetry. It also provides a very nice calibration of the signal. It tells us sort of what's the height of the sideband that one observes if there's one phonon in this cavity, or two phonons, or three phonons. We also do a lot of characterization to understand the power handling, the heating effects in this device. And I won't, in the interest of time, I won't really say much about this data, except to say it's kind of all makes sense with what we know about standard optical spring and optical damping effects, and a very simple model of thermal heating inside the device. But at the end of the day, we typically operate with sub-microwatt laser excitations. We're getting tens of sideband photon counts per second. And the device is typically cooled to a mean phonon number of about 1, between 1 and 2, depending on the exact circumstances.
5 minutes.
5 minutes, wow. Okay, good. So then I'll move on quickly. So in order to access some more interesting physics, we don't want to just focus on the mean photon count rate, but instead look at the G2 of the sideband photons that we're counting. And if you're just counting sideband photons, of course, you're entitled to just plot the G2. But if you want to say that these photons detected at the SPD are reflections of the phononic state inside the acoustic oscillator, the mapping between those two is a little bit different depending on whether you're driving the cavity with a red detuned beam, in which case expectation value of normally ordered photon operators is the corresponding normally ordered phonon operators. On the other hand, if what you're measuring is the sideband photons produced when the cavity is being driven by a blue detuned laser, then what you're measuring is the anti-normally ordered phonon correlations. But in any case, this is the data. These are the fits to the expectation for a single acoustic mode in a thermal state. We have enough data, though, that we don't have to just stop at the 2 photon correlations. We can also look at the 3 photon correlations, where this is the time there's an initial click at t equals 0, and then we wait for a certain amount of time, and then another time after that are these 2 axes, and the histogram of photon counts satisfying these delays is shown here, along with the theoretical fit for a thermally populated acoustic mode and the residual here. We can also look at quadruples of photon counts and the corresponding 4 phonon correlation. That results a solid data cube of 3 different delays. We take that entire data cube and we fit it, but for display purposes, I'm just showing you one slice of that cube for the red detuned light and the blue detuned light. And In all of these cases, the fit parameter is the height of the relatively straightforward exponential function that's expected. And those agree very well with what you'd expect for the correlations coming from a thermal emitter. We can take that big chunk of data where essentially the story is complete. We can also slice out post-selections of that data, look at other statistical measures, but they don't necessarily add any new physics, and they all are consistent with the idea that the acoustic mode is indeed in a thermal state. And this is a state with no particularly quantum features, so we would like to move on to some more advanced measurements. The one that, given this short amount of time, the one that I'll tell you about is where we just add a linear drive to the acoustic mode. This is done just by sending in two lasers that make a beat note at more or less the resonant frequency of the acoustics. And we also send in a separate measurement laser whose job is just that if the acoustic mode is vibrating, sideband photons are produced, and we count those. Our interest in making high amplitude coherent states is partially related just to doing quantum limited measurements in the same way that one would like bright coherent states of a laser to do quantum limited optical measurements. But there's also some proposals that such high amplitude coherent states could provide interesting tests of space-time geometry, even at the Planck scale. The experiment works along the following lines. We sweep this beat note frequency, and we just count the rate at which we see sideband photons as we drive it harder and harder. This is the raw data. This is the height of those fitted Lorentzians. From our calibration, we know that here we're sort of driving the acoustic mode out to about 20,000 mean phonons. And just qualitatively, we can see that the line shape is constant, the amplitude is growing with the strength of the drive. This all looks like the state is being kept relatively pure. But in reality, any kind of parameter noise in the oscillator in these drives could spoil the purity of the original state. The original state, remember, is a thermal state with about 1.5 phonons in it. We would like to know when we displace it, how much noise are we adding? Do I have a minute left to show some slides?
Yeah, 1 minute, yeah.
Okay, great. So to do that, we look again at the G2 of the sideband photons, but now as a function of how hard we're driving the acoustic mode. And when there's no drive, we just see what you'd expect for a thermal state. As you drive harder and harder, this data looks more and more like what you'd expect for a coherent state. But even with a large drive, if we zoom in, we can see a very clear signature of sort of the remaining bit of thermal noise on top of the coherent state. So we can resolve G2s definitely down into part per thousand. So to get some sense of how much we can use that as a measure of the purity of the state, we measure, this is now G2 minus 1 on a log scale, as the system is being not at all driven harder and harder and harder. And these time traces show pretty good fits. I don't have time to talk about that. But if what we extract is just the 0 time value of the G2 correlation, it undergoes a smooth transition from 2, what you'd expect for a thermal state, to a value of about 1, which is to say that you take some kind of thermal noise blob in phase space and have displaced it by much more than the size of the thermal blob. But has the thermal noise blob gotten bigger? This is the same data shown on a log scale, again with the black line as the prediction for what would happen if you started with a thermal noise blob and just displace it without increasing the size at all. So this data indicates that out to at least sort of mean coherent phonon number in the tens of thousands, essentially no noise has been added. Okay, so that's a relatively pure high amplitude coherent state. I think I'm out of time, so I will skip over, except to say very briefly, we have some paths to making much higher phonon lifetimes by tweaking the cavity device geometry. And we also have a relatively straightforward way to making these devices into indistinguishable single photon emitters, where the single photon is the sideband photon and the corresponding quantum memory is the acoustic state in the cavity mode. And given that this is all realized in telecom optical fibers at 1550 nanometers, this seems like a promising route to some technological applications. So I'll just put up the conclusions here. Again, thank our students and collaborators, and I guess if there's time, I'll take questions.
Thank you, Jay. Very nice talk.
Thanks.
Questions? Yeah. Anupam, you can go ahead.
I think it's Nancy who
Ah,
has her
sorry,
hand raised.
Nancy.
Yeah, hi Jack. Thanks a lot. Very good talk.
Thanks.
So I have a lot of questions, but maybe I'll just stick to one for the interest of time. When you were talking about the mechanical mode being chosen from the laser mode, I was wondering, how does the detuning of the optical mode play a role into the change of frequency of the mechanical mode? And not the optical spring effect, but just the geometry stuff.
I'm not sure I understand the question.
So like here, when you're deciding the cavity length, that fixes the mechanical mode, right? So if you had to pick a different cavity length that was slightly detuned, then what would happen for the mechanical mode?
You pick the cavity length, 10 microns, 20 microns, a millimeter, and then we all know what are the standing waves inside there. And
on
the
resonance, yeah.
Yeah. And so whichever of those cavity modes you pick to drive with the laser, that cavity mode will have a coupling to the acoustic mode with exactly half the wavelength. So maybe I haven't understood your question.
Well, if you're driving it detuned, then you're still coupling to the same mechanical mode.
Yeah, so I guess there's a sort of separation of length scales here. So the cavity line width is maybe 50 megahertz. And the cavity free spectral range is like a terahertz. So when we detune by a few cavity lines to be sitting on a motional sideband, we're still driving that optical mode.
Okay.
Yeah. So all the detunings are very small compared to the free spectral range. So when the laser goes in, it's always driving, this mode, so to speak.
Yeah. Yeah. Oh.
Jacob, please go ahead.
Yes. So Jack, wonderful talk, great progress. I'm particularly interested, in the spirit of this meeting, in understanding how the sideband counting technique that you're talking about gives you indirect information about how non-classical the phononic state you left behind is, or alternatively how non-classical the phononic state was, right? Because a key feature, we need to make non-classical mechanical states. So do you want to talk a little bit about how that's working for you?
So far, everything we see is consistent with, classical quasi-probability distributions, because we're just parking on one sideband and looking at the statistics there. I think as nicely elucidated by people in this field for a long prehistory, and then in the context of optomechanics, nicely by the Painter and Groblocker and Aspelmeyer groups, you would look at pump probe measurements between driving and detecting on different sidebands. And so that's where we would like to head next. But I don't, beyond sort of the standard story involved in those measurements, did you have a...
I mostly meant how far away are you?
Not that far. I mean, we can toggle between red and blue sidebands. In fact, I should acknowledge the students' very hard work. We have done that. They have looked at what we call G2RB, which is like drive on red sideband, detect on blue sideband, vice versa. That's a well-known route to testing things like Cauchy-Schwarz inequality. Students have done those measurements. We have seen Cauchy-Schwarz inequalities violated, but given our filter cavities transmission and the overall statistics, it was sort of at the 1.5 or 2 sigma level. And so rather than talk about that, I would sort of rather wait until we've made a few technical improvements. But yeah, at sort of informal level, we've seen Cauchy-Schwarz inequalities violated in the conditional two photon.
And then at an informal level, what would you estimate to be the coherence time for the non-classical state that you might have?
Well, I think just what you'd calculate from the thermal, the phonon lifetime and the thermal bath, which is sort of 100 microsecond.
Got it. Okay, thank you.
And in the next generation of devices, we think we have a very straightforward route to improving that by about 3 orders of magnitude. Basically, no engineering in these devices went into maximizing the acoustic quality factor. So we have some low-hanging fruit to pluck there.
Antonio, hopefully a short question. We're a bit over time.
Hi. Yeah. I'll be short. Hello, Jack. Very nice talk as usual.
Thank you.
So you mentioned that in passing that you were interested in creating these mechanical coherence states to test quantum gravity effects, right? So at this point, proving the mechanical coherence state was probably the hardest step. So what's the roadblock you could have in doing those tests?
You know, again, we have just sort of taken a little time to look at the numbers involved here, and you know, this proposal, as I understand it, involves characterization of a high amplitude coherent state is interpretable as the non-existence of certain weird effects in the geometry of space-time at the Planck scale, or at least at a certain length scale, depending on how good your experiment is. And first pass at looking at the numbers just on the data that we've taken, this looks like the parameter which is called L sub p in these papers, which is sort of the length scale on which one is probing, the characteristic length scale associated with some nonlinear effect. It looks like we can rule out nonlinearities at the 10 to the minus 19 meter scale, which is the scale that's commonly quoted as LHC having probed. I don't know this physics well enough to feel like I can vouch for these claims yet, but I'm looking forward to learning a bit more about that. So I think the data is kind of in the can. We know how to do these measurements, and I'd like to understand a little bit more about the kind of underlying models and what we could say about the physics in them.
Thanks.
Okay, thank you, Jack. Could you unshare your screen?
Yes.
So we go to our next speaker, Andrew Geraci from Northwestern University. Andrew?
Okay, let me just share my screen. Hi, can everyone see?
Yeah.
Okay, well, I'd like to thank all the speakers for the great talks we've heard so far, as well as the exciting discussion. I'm looking forward to the remaining discussion both today and tomorrow at the end of the workshop. So I'd like to just say a little bit about some of the work we're doing in our group at Northwestern, where we're using optomechanical systems to look for fifth forces that may be related to quantum gravity, as well as dark matter, and looking forward to possible other tests of aspects of quantum gravity, consistent with what's been already discussed quite a bit here at this conference. So I'll start off talking a little bit about our efforts looking at gravity at short distances, and then mention some other applications that we're excited about using similar techniques to look for gravitational waves in dark matter, and then finally talk about some of our future plans for developing methods to do matter wave interference type experiments with levitated nanoparticles, with the aim again of gravitational probes of physics in mind. So we know the standard model does a fantastic job describing many of the basic features of nature, but there's a puzzle that poses an issue for theorists, which is if you look at sort of the relative strength of the four standard model forces, say between two protons inside of a nucleus, you'll see there's about 36 orders of magnitude difference between the gravitational attraction and the electromagnetic repulsion between the protons. And so this has been something that's already been noted at this workshop already. And in theory, it's known as the gauge hierarchy problem, which is connected to why gravity is so small compared to the other fundamental forces in the standard model. And so one can also cast this in the framework of energy scales. And so, for example, if you look at the energy scale of the standard model physics that we know about, say at the Large Hadron Collider, which is at sort of the TeV or 10 to the 3 GeV level, there's apparently no known physics or a vast desert between this energy scale and the energy scale where one would naively expect quantum effects in gravity to show up, which would be at something like 10 to the 19 GeV. And so this requires some extreme fine tuning in the standard model in order to explain a physical value of the Higgs mass that we observe. One of the most popular solutions to this is supersymmetry, and which is still being searched for at the Large Hadron Collider. Other suggestions have been that perhaps this really high energy scale of quantum gravity isn't really a fundamental scale, and perhaps that the real fundamental scale of gravity may be closer to the electroweak scale or down at the TeV scale. And in these models, perhaps this apparent weakness or this apparent high energy scale of gravity is just an artifact of the fact that gravity might be able to propagate in extra spatial dimensions that the other standard model physics that we know and love can't access. And so in this way, there could be these large sub-millimeter, when I say large scale extra dimensions around us, where gravity is basically diluted as it propagates into that bulk, whereas the remainder of the standard model is confined to our normal three-dimensional world. So, I mean, either one of these scenarios, one could expect in an experiment that there could be some deviations that would show up if you were to measure gravity at short distance. And a particular length scale that comes out of these theories tends to be at the sort of sub-millimeter level. And so the types of signals that one may expect would be a change in the 1/r potential of Newton gravity, or perhaps a new exponential form that would be showing up at only short distances. And so this is typically parametrized in the following way, using the Yukawa type correction to the Newtonian potential. So here I've written the familiar Newtonian interaction between two masses, m1 and m2, separated by some distance r. The coupling constant is the Newton constant. And then the idea with these physics beyond the standard model, some of which may be related to quantum gravity or string theory, would be that there'd be a correction piece, which is what's showing in parentheses here, where we have some term here, alpha, which is basically a dimensionless number that characterizes the strength of the new interaction relative to 1, the strength of gravity. And then there's some length scale. This lambda here is some exponential length scale. It's the Compton wavelength, essentially, of the new particle that's being involved in this interaction. And if you're below this length scale, you can see these effects. And apart from that, it dies off exponentially. And as I mentioned, there are several models, including supersymmetry and string theory, as well as these other large dimension models, which kind of naturally predict that the sub-millimeter range is where one might start to see some of these type of effects. So if I look at sort of the landscape for tests of this non-Newtonian form of the inverse square law, or the 1/r potential, we can plot it here on a graph showing over a wide range of length scales. So here I have this again, this form of this exponential correction. On the horizontal scale, the length scale in meters, going all the way up from astrophysical scales at kind of planetary scales down to sub-micron scales in the laboratory. And in the vertical scale here, I have the strength parameter relative to gravity, where 1 is this dashed horizontal line here, so that indicates gravitational strength. And so if you can see sort of at Earth-Moon distances, there have been some very precise lunar laser ranging experiments, which really have shown that there's really no correction to this 1/r potential at the level of about 1 in 10 billion. And so this is, of course, quite a nice confirmation. But now if you move to laboratory distances down at, say, the 10th of a micron level, you can actually flip the sign of the exponent. And in fact, you could have a correction here about 10 billion times the strength of gravity, but there would be no experimental evidence that would contradict the presence of this type of new interaction. And so these experiments are difficult in the lab for a couple of reasons. One of them is just the weakness, again, of the gravitational force. If I look at sort of how the force between two masses scales, when I sort of scale down the size of the system, just taking as a cartoon example, say if you have spherical masses and you bring them as close together as possible at some separation distance equal to their diameter, then if you plug in the fact that the mass of these objects has some finite density and some size to it, the Newtonian force actually goes like the positive 4th power of the separation of the size scale of the system. And so as I scale things down, if I take material that's about as dense as I can find on Earth, or say 20 grams per cubic centimeter, then in the sub-millimeter range, for example, at the 10 micron scale, the level of force here we're trying to measure is 10 to the minus 21 newtons, or zeptonewton. So it's quite experimentally challenging. At the same time, as has also been pointed out in several other nice talks, there are many other background forces which tend to get more significant as you bring things closer together. And so one notable example that's sort of interesting in its own right is the Casimir effect due to macroscopic manifestations of quantum vacuum fluctuations. This can cause attractive forces between nearby surfaces, for example, even if you have no electrical potential difference between the surfaces. And then there are also sort of more dirt-like effects or surface inhomogeneities that can cause spurious backgrounds. And so, for example, if you take a good conductor, like even something like gold, you can have local polycrystalline sections in the material, which can give you different work function variations over the surface of the material on sort of the micron length scale. And so if you look in detail at these things, you find that even though in Jackson you learned that conductors are perfect and have equipotential everywhere, in reality they tend to have more of these microstructured patch potentials. And so these types of signals can indeed produce a challenging background to deal with in these short distance experiments. So now if I zoom in kind of on the smaller length scales here of the same sort of parameterization here with this Yukawa type correction to gravity, now I'm plotting the interaction length from 100 microns down to about 10 nanometers. And here this alpha is going from gravitational strength here at the bottom all the way up to about 10 to the 15 times gravity on the top. At the largest length scales, the best limits come from precision torsion balance experiments that are done at the University of Washington. The kind of 10 micron length scales, there have been limits from micro cantilever experiments, and then at shorter distances yet, there have been limits from adaptations of experiments designed to look for the Casimir effect. And some of the theoretical predictions that I mentioned in the first few slides are shown here in these shaded pink and green areas here over to the right for some targeted interesting area to search for. But so all of these systems have been using some kind of mechanical oscillator, whether it's a torsional fiber or a micro cantilever beam or some other sort of microfabricated torsional oscillator. And so the sensitivity in those limits, in addition to having to deal with these background effects, the force sensitivity is typically limited by thermal fluctuations or thermal Brownian noise, just the same way that a piece of dust gets kicked around in a fluid by fluid molecules in sort of a random Brownian motion. If you have a oscillator in contact with a thermal bath, you can figure out from the equipartition theorem that there's some minimum force you can observe in the presence of those random thermal fluctuations that goes like KT, the thermal energy, times the spring constant times your measurement bandwidth over the product of the mechanical quality factor and the resonance frequency of the system. And so in these types of gravitational tests, there's some finite, there's some damping in the system due to the fact that you're clamping onto some sort of solid state structure. For example, in the cantilever type sensors, you have surface imperfections and internal materials loss, things like thermoelastic dissipation. And so this is where the optical levitation technique really provides some clear benefit, where now we can sort of decouple these materials like deformations and loss mechanisms from the force sensor by suspending a dielectric particle just using radiation pressure. And if you can do this in a high vacuum environment, now you can circumvent these materials related loss mechanisms and really realize a nice clean force sensor that's an oscillator suspended by radiation pressure. So our group and many other groups are using these as sensors, as well as for other tests of quantum mechanics and quantum foundations. So in our group, for example, we've been able to demonstrate that you can do calibrated force sensing at the level of a few zeptonewtons in a standing wave optical trap, or optical lattice as we call it. So in our case, we've shown that you can measure down to a few zeptonewtons in the case of if you have a neutral particle. Most of our particles tend to be electrically neutral, which, as it's been pointed out, is very, very important when you're trying to do surface force measurements or measurements of small distances. Occasionally we have one or two excess electrons on our particle, and we can actually use this to calibrate the sensitivity by applying a known electric field and then making sure that we're actually able to see forces at this small level that we're claiming to be able to test. So we're building an experiment or operating experiment where we have a nanoparticle that's trapped up against a thin mirror membrane. So we have a gold-coated 200 nanometer thick membrane of silicon nitride where we retroreflect a laser beam off the surface, and then we trap a nanoparticle of a few hundred nanometer diameter in one of the standing wave antinodes, or bright spots in this cavity. And then behind this cavity, we have a mass device which consists of different materials of gold and silicon sections to provide a density modulation. And so when we move this device, then the density modulation will impart a force on the particle, and then we can read out the displacement to figure out the gravitational interaction. And so our goal is to be able to carve at least a few more orders of magnitude deeper into this search at sort of the micron scale by keeping the particle within kind of micron range distances from the surface. And I should mention that there's also parallel work going on in different trapping geometries, both at Stanford and Yale. We heard already from David Moore, and then we're also going to hear in the following talk some exciting progress from a group from the Stanford group in Georgia Grata's lab. So in our group, we trap the particle initially in a dipole trap, counterpropagating beams, and then we can transfer it into an optical cavity trap where the measurements for gravity will take place. Our test mass is a 300 nanometer diameter silica bead. Here's a photo showing more of the actual setup, where we have behind a mirror, we have the actuator that moves around our segmented mass to provide a signal to the test mass or nanoparticle. This is a picture of the fabrication technique that we have for producing the source mass in our system. Basically, we take a silicon wafer and we can etch trenches into the wafer and then fill in the trenches with electroplated gold. When we do that, then there's a sort of a corrugation that's still appearing at the top surface of the gold. We don't like this because it would also represent a modulation of any kind of electromagnetic interactions. And so we have a nice density contrast between the gold and the silicon to provide a gravitational signal, but we don't want any modulated Casimir or other kind of electromagnetic interaction. And so we basically take our mass and flip it upside down. We polish away the back of the silicon. This is a cross cut that we did at a focused ion beam in the middle of that process, where we're basically removing the silicon wafer, and we stop this process when we only have about 1 or 2 microns of silicon remaining above the gold. At that point, we metallize the top surface, and then this provides a nice uniform surface to impart the gravitational density signal on the test mass. So to do this experiment, we need the sensitivity. We also need the source mass. We also need the particle to be very close to the surface. And there are some challenges, as has already been identified, with operating force sensing with these particles near surface. And so we've developed a technique now to load the particle near the surface in a way that's fairly robust. And so basically what we do is now have a method where we can retroreflect an optical lattice, essentially starting off with the particle in one trap and then essentially inserting a mirror into the trap and transferring the particle in situ from one trap to a trap at some distance away from the surface. And so, for example, here's some data in our most recent results where we've transitioned a particle from an initial trap, which actually in this case consisted of a single beam tweezer, into a optical lattice trap. In this case, the particle is at the first antinode of a telecom wavelength beam at about 400 nanometers away from the surface. And you can see as the trap transitions, we get a massive shift in the frequency of the oscillation mode along the axis of the laser, where now it becomes tightly confined in the lattice potential of this trap. Once we do that, we can actually scan over the surface of the trap, over the surface of the mirror, actually, and also adjust the distance from the surface to the mirror, going in the different antinodes. And we can measure the force sensitivity. So we've been able to measure attonewton level forces so far at kind of intermediate vacuums of 100 millitorr or so. But we see no significant excess noise or degradation of the sensitivity in the closest points of the surface, which we think is encouraging for these tests. And so at each one of these points, we can furthermore scan the position of the particle in the plane parallel to the surface. And so what this allows us to do is essentially make a map over the surface of whatever forces may be present to help. And this could be quite useful to characterize these kind of surface effects due to patch potentials or other kind of effects. And so we expect, even though the work we've done so far has been and at the kind of attitudinal level, we are already implementing the feedback cooling techniques that our group and other groups have developed to and expect that we should be able to do similar tests eventually at the level of zeptonewtons, similar to the sensitivity we've seen in our trap previously. And so the hope would be then to kind of map out the nature of any sort of disturbances or imperfections in the surface in a way to better understand the signals and potentially subtract out any non-gravitational effects in these experiments. So we're gearing up now to hopefully have some first results soon from gravitational tests at this sort of micron or submicron distance. But I wanted to shift gears a little bit at this point and mention another application that I'm excited about that we're developing, which is actually to try to use these levitated particles as a method of detecting gravitational waves, in particular at high frequency. And so this is a very exciting time in the community where we've now demonstrated that we're actually able to see gravitational waves, and the prospects for mapping out the gravitational wave spectrum of the universe is, I think, quite exciting, especially in many different frequency bands. And so the idea with the levitated particle is it's sort of a optical version of the original gravitational detectors that were pioneered by Joe Weber, where he basically had a big piece of aluminum that would ring at a certain frequency. If the right frequency gravitational wave would come along, and you could measure, a strain in that material. And so here what we do is have a cavity, can be much shorter than the cavities, for example, used in LIGO. You trap a particle in the cavity, and then the gravitational wave will come and create a disturbance where the physical length of the cavity will change. And this will in turn kick the particle around into some oscillation. And so there's still a resonant effect in the sense that you can try to match the resonant trapping frequency of the particle in the cavity to the gravitational wave frequency. And when you do this, you can get quite good strain sensitivities. For example, in a 10-meter cavity, something on the order of 10 to the minus 22 per root hertz, but only at high frequency. And so the idea would be that these systems wouldn't really compete with the LIGO type detectors in the band if they're most sensitive, but they would rather extend the sensitivity up to higher frequencies. Where at higher frequencies, the LIGO style interferometers are limited by photon laser shot noise. In our case, we expect to be limited by thermal noise in the sensor. These two different noise sources have a different frequency scaling. And so while the LIGO sensitivity tends to get worse at high frequency, we expect ours to actually improve. And so we're also investigating with
4 minutes.
Oh, perfect. Thank you. So with our collaborator, Peter Barker at UCL, potentially implementing a fiber-based approach here, which would allow us to extend the length of the cavity without the need for larger, kind of higher cost optics, provided that we can keep the noise in the cavity at a level that's manageable at these higher frequencies. And so that's work that's still ongoing. So one of the science targets at these high frequencies that we're really going after is actually dark matter. And so there's a lot of evidence for dark matter, and it's really, I think, one of the biggest hints that there's some physics out there beyond the standard model. Dark matter could exist over a variety of mass ranges spanning multiple orders of magnitude. And so in particular, one of the signals that we're looking for would be axions, and another would be primordial black holes. And so if I have solar subsolar mass black hole in spirals within our galaxy, this could provide one science target that would be visible at these higher frequency bands. And also another signal would be axions, which could annihilate in clouds that they form around black holes within our galaxy, so within, say, 10 kiloparsecs, and two axions annihilate to form a single graviton. That gives you a monochromatic signal, basically at the twice the axion mass. And so if you have a gut scale axion, the frequency of interest is about 100 kilohertz, which is kind of right in our sensitivity band. So this purple band here is showing how we would be projecting to extend the frequency of gravitational detectors up above the LIGO band to look for some of these exotic perhaps dark matter related things. So these are all, everything I've mentioned so far at least has been sort of where the sensor itself is sort of in the classical limit. But I think it's interesting now that we're able to access the quantum regime as we've been able to do for quite a long time now with individual atoms. What can one do in the quantum regime? So it's, I think, remarkable progress in the last decade where now we can put things that you can look at 60 microns across here really in the quantum ground state of the vibration. And then this just shows some of the results that were happening over the last couple of decades. Of course, there's the landmark result that we heard about this morning from Marcus Asselmeyer's group. We're now with the Levitated systems community, we're able to access into the quantum limit. And so one prospect I think that's quite interesting to think about is matter wave interference experiments. So this is along the lines similar to one of the ideas mentioned by Hendrik earlier this morning. So we'd like to basically do experiments where we can prepare a nanoparticle in some cold ultra cold initial state, and then essentially drop it in a free fall, let it interact with a grating of some kind. In our case, it would be a light grating we have in mind, and then use this to generate an interference pattern when we repeat this experiment multiple times, where this interference pattern would actually be sensitive to accelerations with perhaps nano-G or even better acceleration sensing capability. If one could do this and one did it near a surface where I had some sort of gravitational signal, again, from some source mass, one could imagine mapping out, again, this parameter space for these Yukawa type corrections to gravity. In particular, with the matter wave sensor, we think we could carve quite deeply into the parameter space at the sort of few micron kind of distances using this technique, again, provided that the other kinds of backgrounds could be controlled in a reasonable way. And then, of course, at this conference, there's already been a lot of discussion about similar techniques potentially being used with creating macroscopic quantum superpositions of nanoparticles for these very interesting tests of potentially looking at quantum entanglement. And of course, there are many challenges, and it's been great having lots of discussions about these types of things in the workshop, so I won't say much more about that in this talk. So I just want to mention a couple of very brief things that we're doing, different techniques to potentially enable useful tools for doing these matter wave experiments. One is new cooling techniques we're working on, where we're trying to couple nanoparticles actually to cold atoms as a way of potentially also bringing them into the quantum regime. Theoretically, this should be possible even from room temperature, and that's something that's ongoing work. And we're also developing techniques to load the particles directly in a high vacuum and recapture the particles, which would be really useful, I think, for some of these techniques, where one could actually use the same particle, because as you know, when you build up an interference pattern, one particle at a time, you really need to have a lot of flux or throughput to really do this experiment well. And so we've done some preliminary work on using lasers to try to slow the particles down, and eventually be able to catch and recapture them all in the high vacuum limit. So that's ongoing work right now. So I'll quickly go over that since my time is sort of running out. So with that, let me just summarize. So we've demonstrated calibrated sensing down at the zeptonewton level using these levitated particles, and are running an experiment now to look for gravitational new signals at the micron scale. We're building a prototype 1 meter gravitational wave detector using levitated particles, and then in the future hope to be able to do some of these matter wave interference experiments, which may ultimately allow us to answer other interesting questions about gravity and entanglement, and whether there's any novel gravitational decoherence signals. And so I wanted to just acknowledge the people actually doing the work, and thank our funding agencies, and thank everyone for your attention.
Thank you, Andrew. So yeah, we're a bit over time, but let's take a few 3-4 minutes of questions. Anupam, please.
Hi, Andy. Very nice talk, as always. So, so it seems gradually that from your talk as well as from Dave's talk that the patch potentials, the Casimirs, these are the real background for any experiment we would love to do at very, very short distances, including quantum gravity or classical gravity even. So maybe is there any broader plan one can make? I mean, because we cannot get rid of them, and it's not that the same sample is going through my experiment. Maybe I need to drop billion samples or 1,000 samples.
Or maybe the sample rotates, or it looks different from one shot. Yeah, no, it's a good question. I think, so one approach that we're taking, at least in our short distance test, where we hold on to the same particle for more or less the entire test, is to try to make an active effort to characterize the surface and sort of understand in more detail what the profile of that looks like and what aspects of that are independent of whether my mass is nearby and which aspects depend on whether the mass is nearby, to try to separate out effects that may be related more to the signal we're looking for compared to the backgrounds. But so yeah, so it does seem, I was encouraged, at least from our most recent experimental test, that we didn't see any excess noise or any significant limitations at the surface at the level we've looked at so far, but we haven't really done the experiments yet at our full sensitivity. And so I think it'll be interesting to see, you know, to what extent that really limits us with the size scales and distances we're working at as compared to with what some of the other groups are working at with larger particles.
Any more questions? I see no hands raised.
You know, I can't quite figure out how to raise my hand, so maybe I'll just jump in.
Go ahead. Yeah.
This question around the ubiquity of electrostatic disorder and the like, I can't speak to Casimir, but one idea that Dave Moore and I have been developing is the possible use of levitated liquid helium drops. As a material, liquid helium has essentially the density of condensed matter and zero electrostatic disorder in the form of, you know, charge defects of any kind. So it seems promising. It's something we're excited about. And obviously there are other issues and the trade-off, but it's at least something to keep in mind.
Yeah, that's a nice idea. And I think also the purity of the materials too, even in the case of these other in the fabrication methods and so forth, might also make some improvements just from other, but I think that's a great idea, the helium. Yeah.
Thanks.
Okay, so no more questions. We go to the next talk by Chas Blakemore from Stanford University. Chas, what was yours? Thoughts? Chad, wait, you're on mute.
There, are we here now?
Oh yeah. Now we hear you and we see your slides.
I apologize for that. But it has been, I'd just like to thank the organizers for the invitation. It's been a pleasure to hear all the great progress people are making in this field. And it's especially nice to talk right after Andy, because he introduced a lot of stuff that I won't have to talk about. But today I'm going to be talking about one of the, or really the first realized search for these new long-range forces at the micron scale using optically levitated microspheres. And I've done this work under the direction of Giorgio Grata. I just like to first, before talking about anything, acknowledge that this is always a team effort. You know, there are many different people that operate the apparatus, many people that do the data analysis, and we all yell at each other to make progress happen. But pretty much every individual in this photo was involved at some level in some way. So I'll give a little bit of overview of my talk. I'm going to give an introduction, which hopefully will be short given the talks that Andy and Dave have given earlier today. I'll talk a little bit about the test and source mass characterization that we use in our experiment, and then we'll dive right into the measurement and the interpretation and future improvements. So the basic idea is you have Newtonian gravity and you have another term, as Andy alluded to. There's all sorts of different theories that would add a Yukawa type term, but generally speaking, if the force carrier is massive, if this force carrier mediating a new interaction is massive, you end up with a Yukawa potential. And so one thing I'd like to point out is that this is just a particular parameterization that very much allows comparison across a huge number of scales, from astrophysical scales down to laboratory scales. But generically speaking, investigating any deviations from a 1/r potential is interesting in and of itself. So this plot looks suspiciously like the one that was on Andy's talk, but it's slightly outdated, but it tells most of the story. There's some great measurements of lunar laser ranging. And I should say that this plot doesn't include the microscope result from the European Space Agency that like cuts out a huge, depending on how you interpret their result, cuts out a huge swath here, but it generally tells most of the story. But as Andy was talking about, there's in this short range force regime, measurements are terrible. Well, I mean, they're good measurements, but barely anyone can see gravity. And so zooming in on some of the best measurements that can actually see gravity are these Cavendish torsion balance experiments at the University of Washington. There's also some microcantilever experiments, but then there's a lot of parameter space to explore here, and especially like the 1 and 10 micron scale, we haven't even seen forces of the scale of gravity. So there's lots of good work to be done here. So the idea of measuring gravity at short range with microspheres in particular was proposed by Andy, and the basic idea, you probably even saw this plot from his talk, that you position a microsphere within this cavity, you have some source mass and you move it around, and that oscillating or that modulated density induces some signal, and you look for correlations between the drive motion and the response motion, more or less. And so the way we do that is with so I'll talk a little bit about our system now and how we do that. And so first, I would like to just take a step back and remember Arthur Ashkin and some of the incredible work that he's done. And in one of his original papers, I mean, there's many, but he has a little statement where he's like, thus, optical levitation with feedback can be used for blah, 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 including measurement of gravity forces. So, I mean, every time I read one of Ashkin's papers, I go back and like, I spent 2 months, trying to understand this when Ashkin just knows everything. He was brilliant, and I think my PhD could have been done a lot faster if I had read all of his papers in more detail once a year to learn everything. But we have a style of optical tweezers that's very much like Ashkin and like Dave Moore's group, where it's a vertically oriented optical tweezer. So as Dave mentioned earlier, that this has a nice situation where it's using the minimal power essentially to stabilize the microsphere against gravity. In particular, the radiation pressure of the beam stabilizes the position of the microsphere. And so we use a 1064 nanometer beam. We use a few different types of microspheres, but they generally range from, the two most frequent types that we use are 2.5 micron radius and 3.8 micron radius. But just to give you kind of an order of magnitude of the numbers, you're basically using the deflections of the outgoing beam as a measure of a force applied to the microsphere. And if you just work in the kind of ray optics limit with some efficiency factors to fudge around the numbers, you get for a milliwatt of power, which is about right to levitate a 2.5 micron silica sphere, and a milliradian of displacement, or of angular deflection, excuse me, corresponds to about a femtonewton of force. So looking at the 10 to the minus 21 Newton forces that Andy was talking about, you need to look for nanoradian level deflections, just as to give you kind of order of magnitude. So this is the full optical system. There are lots of details in this review of scientific instruments paper that, so I won't go over much of it, but basically it's a single beam trap. We use one beam to trap the microsphere, one beam to apply feedback, and one beam to do the imaging. The feedback is accomplished in horizontal directions by deflecting the mirror, and in the vertical direction by modulating the power with a fiber coupled acousto-optic amplifier, modulator, excuse me. And the position of the microsphere is imaged by looking at both the forward scattered light and the retro-reflected light. So the microspheres are not AR coded, and spheres of order the size of the wavelength. So there's a non-negligible amount of retro-reflection. And as other people have alluded to, retro-reflected imaging works actually quite well. But we do it in a particular way where we just look at the phase of the retro-reflected light. If you just imagine a planar reflector, as it moves up and down, changes the path length, which gets encoded in the phase, and we interfere it against a reference wavefront. Same for the transmitted beam, but the superposition of the reference wavefront and the transmitted wavefront go onto a quadrant photodiode, and then we look at the power distribution among the quadrants. So as again, Dave and Annie alluded to, there's stray electric fields, and electrostatic backgrounds in general can represent a huge background. So our entire trapping region is shielded by 6 identical electrodes that sort of make a cubical cavity. And each of these electrodes is like a pyramid, essentially, that has a borehole through it, so you can optically and mechanically access the central region. So this is a cross-sectional view of that, essentially, looking horizontal, so we're looking down at the trap. And there's a few different things here, like the main nanopositioning stage, which has our attractor mass, another nanopositioning stage over here that can be used to position other mechanical devices within close proximity, and then some other optical accesses for auxiliary imaging and that sort of thing. One important thing is we can actually use this well-known geometry of electrodes to drive known electric fields, assuming finite element analysis gives you, a valid field value for a certain configuration of voltages and geometries. So we can apply known electric fields and calibrate the response. And usually in our particular setup, the microspheres are charged after we trap them. And so we tend to discharge them with UV photons. And as Dave mentioned, if you apply an oscillating electric field, say between 2 of those 6 electrodes to push the microsphere back and forth in one direction, you watch its response. And as you're flashing it with UV photons, the response decreases in a step function. And this unit step size corresponds to a single electron being discharged from the microsphere at a time, until you get to a point where there are an equivalent number of electrons and protons on the microsphere. And we're pretty confident that the unit step size is a single electron, because we see, although not in this particular iteration, you see multiple step size. So you see a 1 unit step, a 2 unit step, a 3 unit step, a 4 unit step. And it's hard to imagine some process that's only giving you, say, two electron discharges simultaneously, or 3 or something like that. And I should say that this method also allows a direct calibration. Since we know the applied electric field and we know the response for a particular for a fundamental charge, you can directly correlate the amplitude of your response to the actual applied force of the microsphere. So it's a direct empirical calibration. So it's just a picture inside of our chamber, the obligatory picture, if you will. Here's our electrode cube, which is suspended over. You can see the top parabolic mirror, which recollimates the beam and sends it out to the right. And there's the input beam comes below all of this stuff from the left and hits another mirror down here. There's lots of stages and lots of wires inside of the chamber. So now we can talk about actually the short range measurements. Now I have an idea that there's an optical trap inside of some electrode cubes. Now, what do you do with this? So I like to preface this when I'm talking to non-scientists that it's like a ball and a stick. You have a ball sitting there and you have a stick close to it, and you move the stick around and look for the interactions between the ball and the stick. And that's more or less the whole story of the measurement. Things get more complicated when you start to think about patch potentials and electrostatic backgrounds and stuff like that. So we also introduce a freestanding shield in between the two. And I'll talk a little bit about the fabrication of all of these. But the basic idea, again, is modulated density close to a microsphere, move the modulated density, look for a response. So our microspheres, we can actually levitate them in situ. We have this active feedback system. We say, hold the microsphere at a specific spot by modulating the optical power. Then we apply a large electric field, some non-negligible portion of the gravitational force, holding the microsphere there against the radiation pressure. And then you measure the resulting modulation in power induced by the active feedback. And then you can extrapolate this relation under very, very extremely reasonable assumptions of linearity in the photodetectors and how photon fluxes correspond to radiation pressure. And you can extrapolate this all the way down to 0 optical power to get and then you just end up with an equation, QE equals mg, solved for m, relatively straightforward. And we find some mass of the particle. And in addition, we can also image individual particles. This was a surprisingly hard thing to do, but basically you have this microsphere sitting here and you take your stick, and instead of poking edge on, you go below and you shoot the stick under really fast, blocks the beam, and then the microsphere falls onto the stick. And you can take it out, look at it under SEM, compare it to calibration gratings, and get a good size. And so we have a pretty good understanding of the mass and density of our microspheres as a result. And one interesting thing we can just really quickly comment on that is the density from these measurements is exceptionally different from what you might expect. So for fused silica, it's about 2.4 grams per cubic centimeter. The manufacturer tells us 1.8 grams per cubic centimeter. And our measurements with these 3 microspheres indicate more like 1.55 grams per cubic centimeter. So just one thing to note, that in situ measurements of the particles that are being used for these types of experiments can be critical. So of course, we did all this careful characterization of one type of microsphere and then decided to use a different one that was bigger. Thankfully, we were also able to do the same type of SEM imaging. We weren't able to do the same correlated imaging where we measure the mass of one microsphere, capture that one, and then look at it under SEM. But given the consistency between the population of spheres, we just took a bunch of the ones that we used to trap, put them on a silicon wafer, put them in the SEM, and did some population statistics. And we find that the measured radius is essentially exactly what the manufacturer tells us. And this particular manufacturer, which is different than the previous one, has a density that more closely corresponds to what you might imagine for these Stover, what's usual for the Stover process spheres. So even with the spheres that were less dense, their radius was right. So in general, we've just taken the approach that we assume the size given to us by the manufacturer and measure the mass, and then you know the density and you know the relevant properties of your test mass. Okay, now we can talk a little about the attractor mass and what we use to source this. So our attractor masses, much like Andy's, are essentially modulated gold and silicon, kind of a similar fabrication technique where you etch trenches in silicon and then electroform gold inside the trenches. But the way we approach this is we have sort of a diving board that sticks out, and then there's a piano key structure at the end, more or less. And you can see that here. You can see some typical dimensions. The edge of the attractor is about 10 microns tall. You could make it taller to get more mass, essentially close to the microsphere, but at some point, as it gets larger and larger, the top edges start clipping into the beam and you get lots of optical backgrounds. And then we take this device and then we sputter gold over the top to minimize residual electrostatics. And so all of this is an in-house fabrication. We do this at the Stanford nanofabrication facility. I do a lot of it actually. So this is a picture of a device that was made by one of our collaborators first, and then we've made lots of devices that are similar. We also recently developed a entirely new, not entirely new, it uses well-established fabrication techniques, but this particular type of geometry hasn't been done before. And the idea is we make this sort of L-shaped feature in silicon. So again, it's a diving board type, big, long, very high aspect ratio, but it has this L shape. So sort of like a pocket, which you saw before in that schematic diagram. Some characteristic dimensions are shown here, but the size of these sidewalls, for instance, limits how close you can get to the microsphere, and how tall it is also limits how close the shield structure can get to the beam before it starts to interact with the optical field. And just like with the attractor, we sputter gold all over this device. And so just to remind everyone what the geometry looks like now that we've seen these devices in actual pictures, again, this microsphere in a laser, there's this modulated density close to it and sort of an L-shaped shield that sits there to both prevent some amount of electrostatic interaction between the attractor and the microsphere, and also it serves as like a light shield. It blocks or prevents much of the light, the halo or other scattered light from this beam from interacting with the bottom side of the attractor. So this is a picture from that objective you saw, maybe one of the earlier things. It really helps to be able to see what's going on when you want to look at these things. So we, one of the postdocs in our group has spent a considerable amount of time developing a really good microscope to look at these things. And so we can resolve all three, the two mechanical devices in the microsphere at the same time. And we have different optical filters that we can put on this microscope. So you can see when we're not filtering the 1064 nanometer light, there's a big, bright, crazy looking scattered spot from the microsphere. And then you filter that 1064 and you see a nice spherical shadow. And then I should say that this image is illuminated by a 880 nanometer diode. So it's far away. Since we're doing interference measurements, that light doesn't cause any extra background. And I should also say that we usually remove one of the pockets of the shield. So it had these two neighboring pockets. You can just break one off by like poking it with some tweezers. And this allows us to see this optical axis. And then we can align all of the devices. And I will allude to this a little bit later, but the relative alignment between these things, how flat they are relative to one another. And then there's all sorts of different angles. And since Georgia likes planes, we always talk about yaw, pitch, and roll instead of Euler angles. But these things are very, very hard to align. And that limits how close you can get things to some extent. Okay, so now we can dive right into the measurement. So a script for this measurement, well, usually what we do, trap a microsphere, you discharge and calibrate, position these devices near the microsphere, and then you can sit there and almost for an indefinite period of time, just drive the attractor along its density modulation and measure the response. I should say once the microsphere is released, not lost, there are very rare situations where we lose a microsphere for unintended purposes. But once we're done with the set, or once we think we're done with the set of measurements, we'll usually get rid of the microsphere sometimes in an interesting way by turning off active feedback and seeing how long it takes to get ejected from the trap or interesting things like that. Once we do that, we can actually move the devices to interact with the optical field. So we know exactly where they're not, within some precision, we know their position relative to the focal point of the beam, and thus the position of the microsphere during the measurement. And so we have this set up with this modulated density pattern, and then you have a model for what you call modified gravity should be. So when you do a measurement, you need some signal model to compare to. So the way we approach this is you can actually solve for an analytic function between the Yukawa modified gravity between a perfect uniform sphere, essentially of constant density, and a point mass. And then we treat our attractor mass as a bunch of little unit cells there. Each unit cell is a point mass, and then you integrate over it. I mean, it's a sum versus an integral. It gives you nice smooth functions. And you can we've tested this a little bit against the size of the unit cell. And if you make the unit cell smaller than a micron, and if you're at least 10 microns away or 5 microns away, the size of the unit cell doesn't seem to affect at least the smoothness and amplitude of this calculation, or the magnitude of the resultant force. But since we're imaging in 3D, we expect a response in 3D. So this is a particular configuration where the attractor has been put up close and displaced in the Z direction so that we're exciting a force in Z. And this is all simulated for a particular diameter of microsphere, a particular value of alpha, and a particular value of the length scale lambda. And just to give you an idea of the scale of the forces, it's about 10 to the minus 24 for our particular. So Andy quoted a good number, 10 to the minus 21 for this sphere-sphere interaction. But for the sphere with high aspect ratio piano key mass, the scale is a little bit different, but it's around 10 to the minus 24 newtons here. And so once you have this signal, you have your attractor moving back and forth, you know its position because you're measuring its position, you know the microsphere's response, and then you can determine what the expected microsphere response should be. So we move this attractor, say at 3 Hertz, drive it back and forth, and you expect a response at multiple harmonics of this fundamental frequency. So this, as you can see, this isn't exactly a sine wave. There's some non-sinusoidal looking structure in here, and there's also because we're not exactly, we choose to drive not exactly on a perfect periodicity of the density modulation. So you end up with some non-trivial harmonic structure. But the nice part is looking at this in frequency space, each of these harmonics is kind of like an independent measurement of the response. And so we will say drive this attractor continuously for 10 seconds at 3 Hertz, and then repeat this type of integration 10 to the 4 times. And so in this plot, I'm showing the amplitude spectral density of 100 of these integrations. And there are a few things going on in this plot. There's the amplitude spectral density of the microsphere motion when the attractor is not moving. And then when the attractor is moving, that's shown in red, you can see there's a very slight increase in the baseline noise. And there's also a non-negligible response at some of the harmonics. And these little blue lines indicate the level you would expect given a particular value of alpha. I think alpha of 10 to the 10 in this particular case, just as an idea to show that there's some complicated structure among the harmonics. We see some other complicated structure among the response, but they're not the same structure, which will be important later. So I should say that this is clearly there's a background. The nice thing would be if we were to move this attractor around and see nothing and be able to use the baseline noise as a measure of our uncertainty against testing a null hypothesis. Basically, I'll get into that a little bit, but before we do that, let's look at each of the harmonics individually. So
just 4 minutes.
Thank you. We're getting there. So we pick harmonics where the signal strength is greater than the strength of the fundamental. We ignore the fundamental, ignore the 2F, just because we expect those could be significant sources of background. And then there's some weird spectral feature at 29 Hertz, so we ignore the 30 Hertz feature. And then we use a maximum likelihood parameter estimation to determine the best fit value of alpha for each value of lambda that you choose to scan and each harmonic. And so this is kind of what it looks like. We see background forces in each of these harmonics, but they don't look like gravity. So one should note that this plot shows the maximum likelihood estimator as a function of time. So say in this first hour, there are some, I think, a couple hundred different of those individual integrations that are averaged together. And you can see that the maximum likelihood estimator for alpha not only drifts in time, but is significantly different across the different harmonics. And we have a lot of different hypotheses for where these backgrounds come from. But when you have a background like this that seems to drift quasi-randomly, there, stands to reason to ask the question, what do you do with this background? So, the best thing to do would be to mitigate the underlying problem. Sometimes that's not possible. The next best solution is to include a well-informed background model into your parameter estimation, which would be nice if we had a well-informed background model, or you take the unfortunate route, which is you just make some conservative estimate, acknowledging the presence of and limitation induced by the background. And one thing that I should say that people talk about sometimes, or that people do sometimes, is subtracting a background. Never do this. It's a terrible thing to do. I won't go into the details of this, but basically there's a modified profile likelihood procedure where rather than we have some likelihood function where the minimum, the log likelihood, so we're looking at a minimum, not a maximum, is offset from 0 significantly. And so you just say, that sucks. And then you make the delta chi-squared, essentially, if you will, 0 below this maximum likelihood estimator that you've determined to be non-zero, and then you have some single-sided likelihood function. And we can do this independently for the positive and negative backgrounds to get a two-sided limit. When you do that, you get a limit that looks like this. And this is a zoom in of some of the experiments in the parameter space of interest to us. And so I should just acknowledge that if we were to remove these backgrounds completely, just look at our present noise limit, we'd already recover more than an order of magnitude and get a lot closer to some of these measurements. And there's a lot of near-term improvements that we have where a realistically achievable projection represents this purple curve. And so briefly, before I have to finish, I'll just flash over some of the projected improvements. So one thing that we'd like to do that we've talked a lot about is that there are electrostatic backgrounds. So we can actually control the orientation of the dipole by applying electric fields. And in particular, what we've done with a few different publications is applied a rotating field, which you're seeing a little animation of that going on here. And the dipole follows the orientation of the field and kind of wiggles around the field direction and does other things. And so with this, we're starting to get some level of control over the rotational degrees of freedom as well. We've done so this is that likelihood function that I was mentioning earlier. If you add in this is a toy model that we need to validate a lot. We don't have a lot of understanding of this, but if you make some model of the electrostatic dipole moment and couple it with the gradient from a contact potential that's on our attractor system, you can already start to ease the tension with our result with the previous null hypotheses. So I should say in the region of parameter space we're looking at, here, we should see nothing, supposedly, because all these other measurements have seen nothing. So reducing the tension with a null hypothesis by introducing a background model is pushing us in the right direction, essentially. We can also measure vector force fields. So we can change the relative positions of attractor and microsphere over a full 3D grid and then measure the resulting force vectors at each of these locations, and then compare it to finite element analysis. There's some great work that was done in PRA, and so you can refer to this reference if you'd like to know more. We have a many pixel photodiode. Cameras would be great here if we could form images, but cameras don't work at 200 kilohertz usually continuously for real-time feedback without good electronics, and we're not good at electronics. So we're instead going with a 10 by 10 style photodiode, and then being able to perform get a rudimentary image so we can discriminate between scattered light and actual motion, for instance. And we can hopefully reduce the noise to what Dave Moore has shown before. And if we do that, we reduce the noise and are able to make some of these other improvements like passive light suppression with optically black coatings, we can hopefully make some improvements to put us down to this purple curve. And so in summary, I've talked about using an optically levitated microsphere as a precision force sensor, and it's the first test of gravity with this type of apparatus. And there's lots of improvements to be made that should be relatively straightforward. So thank you for your attention. I appreciate it.
Thank you, Chas. So I see Nancy already had raised her hand.
Yeah, thanks, Chas, for this talk and great measurement. I was trying to understand on the slide where you were showing the ASD, the scale of the force there was 10 to the minus 16, whereas
that's correct, yeah.
In the time domain, when you were showing the expected force, that was 10 to the minus 24 in the slide before. So I was wondering if you were to put that here in the frequency domain, where would that line be? From the time
I was very quick to say it, but this one is shown with alpha equals 1, so it's relatively small, and this is for the purposes of demonstrating this. This is with alpha equals 10 to the 10.
So how much below would the line be?
10 to the 10 orders of magnitude.
Oh, 10 to the 10. Okay,
yeah.
But would the shape remain the same, or is it a flat line with a lot of peaks?
The shape would nominally remain the same, but the shape depends slightly on the value of lambda. You get a different harmonic structure because when lambda starts to be around 10 microns, which is the scale of the separation between our devices and the scale of the density modulation, lambda starts to change well, first of all, it's a square wave modulation. Mm-hmm. So you're seeing some smoothed out version of a square wave with some also exponential smoothing from the exponential, or some other extra smoothing from the exponential behavior of the Yukawa interaction.
Got it. And then in the MLEs that you were showing, I don't understand the context of finding an MLE from each harmonic, because I'm assuming that for a given value of alpha, you get a spectrum, right? So like why estimate MLEs from each harmonic separately?
Because the response of the microsphere to different operating under the assumption that it's like a harmonic oscillator and it's linear, it responds independently to these different frequencies. So it's just like talking about rather than fitting a sine wave in the time domain, you're fitting the non-sinusoidal with the complicated structure in the time domain. It's just more where you choose to interpret your information. And when you look at it in the frequency spectrum, each of the frequencies is kind of independent. You're absolutely correct that there is some predictable level. I don't want to say level structure because it's not an AMO thing, but there's some predictable ratio of height.
Relative amplitudes of each harmonic.
Correct, yes. Yeah. But the response of the microsphere at that frequency is more or less an independent measurement. So in a perfect world, we would fit all of the harmonics simultaneously. They'd all be noise limited, and we'd just be able to say, we're at our noise limit. Everything is great. But this was an approach that we took, given that we see different backgrounds in all of the harmonics. So for instance, if you were to choose all of these together, you'd most likely be dominated by, for instance, this 21 hertz one, which is just massive compared to the others.
Yeah, okay, that makes sense. Thanks.
It's a great question. Thank you.
So thanks, Chas. Very nice talk. So I think it's pretty much in the spirit of Nancy's question. So even in Adelberger's group, once I was talking to him, he sees some kind of like modulation and something which you also see in your experiment. So now my question is, suppose if you didn't have to fit it with the Yukawa potential, but suppose if the potential, there's some corrections and something like sinusoidal correction, how would these corrections would look like? Maybe they're completely ad hoc for the time being, but just to fathom.
No, that's a grein question. So it's one thing that I slightly alluded to, and also kind of a potential advantage of our system. A lot of the previous measurements, as the Adelberger's measurement, for one example, those masses are huge compared to they're very close together, but they're really macroscopic objects. And so compared to like a microsphere, so they're not really as sensitive to different potentials, say that are not Yukawa potentials, maybe higher powers of R or different structures. So that's one advantage that the system has. We chose to interpret these results only against the toy Yukawa model because although I didn't talk about it as much, we have a lot of evidence that suggests these are scattered light backgrounds and electrostatic backgrounds that are contributing at the same level. And for whatever reason, the scattered light background drifts thermally and drifts really, really slowly. So rather than try to come up with some alternate interpretation, we're like, okay, we know that this is a bad background. We know that it's not a new interaction, or we're fairly confident that it's not a new interaction. So let's take the very conservative approach and not try to interpret this under any special thing. But Adelberger's measurement is very nice because they actually measure gravity and they're looking for deviations from gravity. Whereas in the 1 micron regime, we're not even measuring gravity. We're measuring other shit, and then gravity is a lot smaller.
Thank you.
And Andrew had one question, hopefully, quick one.
Yeah, just a quick follow-up on this, actually the same plot on the screen. So with this harmonics and the frequency dependence, have you tried varying the drive frequency much and seeing how the harmonics track that drive frequency? And is there a understandable pattern there? Or?
No, it's a great question. There's no truly understandable pattern. It seems we have tried different frequencies, in particular, faster frequencies cause lots of problems, which we expect they start to induce mechanical vibration of some of the components when we start to move the mass, like this reciprocating mass back and forth really fast. But below a certain frequency, you also start to run into the 1/f noise. So we kind of did some reasonable sampling of acceptable drive frequencies, and there is a difference in the background, same order of magnitude, different harmonic structure. So it really suggests that there's some non-trivial background going on that we really need to distinguish actual motion from whatever these backgrounds are. Thank you all for the questions.
Okay, so thank you, Chas. And we go to the last talk by Ron Folman from Gurion University. Ron, please.
Thank you, Yair. Let me try and share my slides. Okay, I hope you can see my slides. Yeah. Okay, so I actually have to start with an apology, and that is I just joined the session, but I had a good reason, and that is that for some unbelievable cosmic coincidence, in another conference, Atomtronics in Abu Dhabi, I was supposed to give a talk just before this talk. So somehow I was caught between two talks. So I apologize for not being in the session previously. I'm going to talk about the possibility of taking our full loop Stern-Gerlach interferometer, and you see here on the first slide already a picture, a schematic picture of how it looks like, and putting in it, instead of an atom, until now we just put in our rubidium-87 atom, put in a nanodiamond. That sounds quite daunting. And I will try to show you that it is daunting. It's a very challenging project, but when all is said and done, I actually believe that it's feasible, but it will take hard work. So on the left side, you see, of course, the picture of the atom chip. It's been around for 20 years. This is the full loop. I'll explain it later. Of course, the nanodiamond that for us is just a rubidium atom. It has just one spin inside, just one NV center inside. So it's just an atom with a big weight on its back. That's how we view it. I also mentioned here that we're now 100 years since the Stern-Gerlach experiment, and for me, it's a sort of nice historical fact. Okay, so speaking about the 100 years, they went into their lab in 1919. In this building here in Frankfurt that still stands. And actually 2 years ago, to commemorate the event, there was a very nice festival workshop in which people talked about what came of their seminal work, and people produced beautiful, beautiful, or showed the beautiful experiments that really can be traced back to the original Stern-Gerlach experiment. And so, of course, Otto Stern got the Nobel. Yeah, here's Gerlach and Stern, and between them, Lisa Meitner, by the way, who was nominated for the Nobel 48 times, but never got it. So the outline, I have very little time, I understand. So the outline is going to be very basic. So I have no time to describe to you motivations, but I guess that after several days of this conference, you already discussed all the motivations. And I will not really go into detail on what is a Stern-Gerlach interferometer. We've been publishing papers about that for 10 years, so I think you know. And in any case, on Tuesday, it was reviewed by Yair. So I'll call that the Stern-Gerlach interferometer, the atomic Stern-Gerlach interferometer. And I would just like to focus on how we can do a real experiment with nanodiamonds instead of the atoms. I always like to show some pictures from the desert around my university. It's about 1 hour south of Tel Aviv. And sometimes I also take my students hiking and flying. They never ask for a second flight, but I'm still investigating why. Okay, so of course, the idea has been floating around for a long time. So the idea of the nanodiamond in Stern-Gerlach interferometer, the idea of a Stern-Gerlach interferometer has been floating around for a century. But the idea of the nanodiamond Stern-Gerlach interferometer has been floating around for at least 5 years. And so very smart people have been suggesting that we do the full loop, which is actually what I showed on the first slide, by putting an internal superposition of the spin, then split to 2 wave packets by gradient, bring them back with active recombination. This active recombination is very important, and I'll mention it in the following. And then, of course, measure the spin. So no interference pattern, no spatial interference pattern, measure a spin. And of course, I will not talk about motivations, but test quantum foundations, measure gravity, probe exotic physics like Penrose, etc., etc. So the main advantage when I look at the full loop is that it's fast. And the reason that it's fast is that we have very strong forces that we can apply. So if you look at this scheme, what you would see is a pi/2 pulse that puts the internal spin, which let's say call it the initial spin as 2, and puts it in a superposition of 1 and 2. And then, of course, you apply a magnetic gradient, the first of 4 magnetic gradients, which does the splitting, just like Stern and Gerlach did. And then a second pulse stops the relative motion. And you can stop here, actually, let the wave packets expand, and you get special interference fringes. That was the first experiment we did almost 10 years ago. But then, if you want to complete the loop, you reverse the force, you do acceleration back, and then you do a final pulse, which stops the relative motion, because if you want to get any coherence here, you have to have full overlap. That's why it's called the overlap integral. You have to have full overlap in both momentum and position. And that's the duty of the forced pulse. And after that, there are different ways to measure the spin, but the way we do it is actually a 5th gradient, which puts a force on the different spins and splits them. And so we just take then an image and we measure the population in the up cloud and the down cloud, and we know exactly what was the spin population at the end of the interferometer. So going back to the fast operation, because of these very strong forces, you can get a large splitting and then very quickly recombine them again. So for example, at 100 microsecond time, you could do quite a large area. And that's an advantage. It's an advantage because you want to fight decoherence, of course, and the decoherence rate on these nano objects, let's call them macroscopic objects, is very high. Yeah, collisions with the background gas, black body radiation. We'll talk about decoherence a little bit also in the following. Another advantage is that you don't require imaging of special fringes. As I said, the signal is very easy. And so I think that's another advantage. Okay, we have not even produced one loop and people are already talking about more loops. So I just bring it here to show you that people are already thinking about this. Here, two wave packets are interacting via gravitational interaction. And if it's the only interaction, and you measure the two spins, so you have a nanodiamond in each one of these loops, Stern-Gerlach loops, and you measure the spin. Sorry, these are the initial states. These are the final states. You measure the spin correlation, and you can verify that you have entanglement. And these, according to these authors, will take us a long way in proving that we have here a quantum particle, the graviton. So we've been starting to do, with the help of theoreticians, all kinds of feasibility studies. I would call them preliminary feasibility studies. A lot more work needs to be done. So this one is just in print, maybe already published. This one just went on the archive by Ryan Marshman. He's the first author, and also Anupam. You see also here in the author list, and Sugato. So these are two feasibility studies. And we're also happy that Physics World a few days ago caught up on this story and presented it in a popular way. If we ever manage to do this experiment, then we have many, many people to thank for this ability. Let me just review some of them. First of all, you need the largest possible coherence length. You want to cool to the ground state. Now, there has been beautiful, beautiful work by Markus Aspelmeier and his colleagues in ideas on cooling to the ground state, and also realizations, and even ideas on how to go forward without a cavity. And that will, of course, will be essential. Because as I'll show, if you don't have large enough coherence length relative to your experimental precision, you're dead. Also works by Lucas Novotny and Ben Stickler. I heard his talk in this workshop, very nice talk, about rotation cooling. That's also essential. And of course, the beautiful work by Gabriele Tet and his colleagues on nanodiamond trapping and manipulation. All these people have made great steps that hopefully will allow us to realize this experiment. Okay, so the goal is to take, say, 10 to the 7 to 10 to the 10 atoms, carbon atoms in the diamond lattice, and one NV center embedded in the middle. And both these numbers are not random, are not arbitrary. This number is because we actually want the NV to be at least 20 nanometers from the surface. Otherwise, it doesn't have any real spin coherence. And so if you calculate it, you see that your minimum is 10 to the 7 atoms. And this number comes from the fact that only at 10 to the 9 atoms and at 100 micron distance between the wave packets with these two loops that I showed you before, only then gravity really becomes dominant. Especially the spin-spin interaction between the two NVs is what worries me, because I'm not sure that we can screen it. So that's why I'm looking at this number, and I want to be safe from this limit. So that's why this is the range I'm looking for. And the idea, of course, is to use the very strong gradients, and we really need strong gradients in order to push these two wave packets out in the very short time that we are talking about. Let us continue in describing this interferometer. And the first thing I would like to tell you is that we want to do a 1D Stern-Gerlach interferometer. So for those who looked at this and thought, oh, this is a 2D interferometer, no. This is a 1D interferometer where this is the center of mass coordinate, if you like, this is just time, okay? So we're looking at the 1D interferometer, and 1D interferometer is much simpler. This is also what we realized so far in our lab. By the way, some people claim that a 2D interferometer, Stern-Gerlach interferometer, is completely impossible. For example, a paper just came out by Englert about that. We intend to check. Actually, I have to say that I don't really believe his calculation. But we will definitely try and check if a 2D is possible or not. But in any case, because of all kinds of alignment issue, a 1D interferometer is much simpler. So we will talk from now on about a 1D interferometer. So the first thing that we would like to consider is actually coherence times. Spin coherence times. Without that, we have no interferometer because our observable is spin. So it's very nice to see that already back in 2014, Dirk Englund in MIT found that for these very small nanorods, he gets 200 microsecond coherence time at room temperature. So that means that if we want to go for a room temperature experiment, we will have to do it in less than 200 microseconds, okay? So we will actually aim at 100 microseconds. Coherence, as I said already, sets the lower mass bound of 10 to the 7 atoms. I mentioned it. And by the way, if you go to a cryogenic experiment, you can get up to several hundred milliseconds, but there is a caveat. Your cryogenic experiment will continue to cool the nanodiamond as long as there is contact. But the minute your nanodiamond is free to do the interferometer and it is being hit by lasers, then its temperature is going to rise. And people have observed fast heating of these nanodiamonds. There's no good way in which they release heat. And of course, you can heat it all the way to photodegradation of the NV. So heating is a very big problem, and you should use as little lasers as you can. And for that, the Stern-Gerlach is beautiful because there are very little lasers in the Stern-Gerlach. And also our measurement is done without lasers. The splitting of the two spins, that's the 5th gradient I talked about. But if you can somehow use lasers to such a minute extent that you can maintain the original temperature at cryogenic temperatures of the nanodiamond, then you can, of course, go to even hundreds of milliseconds. Of course, there's also special coherence times. Vacuum is not really a problem if you talk about these short times that I mentioned. But you can also, of course, look at other things like black body radiation. Here you see 4 lines. You see we start with a 100 microsecond experiment. And I'll give you more numbers as we go forward. You start with a 100 microsecond experiment at 300 K. And that's the blue curve. And you see that the coherence as a function of separation that you want to give allows you to go to a separation of, say, 100, 200, maybe even 300 nanometer. If you go cryogenic, and again, I explained the problems, then you can even think about 100 millisecond experiments. And then depending on the temperature of the environment, but also the temperature of your nanodiamond, you get the other curves. But if everything is very cold, including the nanodiamond, then you really have no problem even up to a micron, the 100 millisecond experiment. Okay, so we consider now an interferometer between 0.1 to 100 millisecond. And for 0.1, I'm going to use room temperature. And for 100 millisecond, I'm going to use cold temperatures, cryogenic temperatures. And I'm going to look at splittings that range from 100 nanometer for the short experiment to 1,000 nanometer for this longer experiment. So this will be somehow our range. Now, the big problem for us is experimental precision. So this Humpty Dumpty for a minimal uncertainty wave packet is a problem. And let me take you through this equation. It's called Humpty Dumpty, by the way, in a series of papers by Schwinger and Englert and Scully in the 80s. They calculated this. We have continued this calculation into more complicated states. But this is the simplest term. And what you see here is the following. This is coherence. And of course, there's an exponential drop as a function of what? This is the experimental imprecision in position at the end of the interferometer, at the end of the loop. So we try to bring together the two, to overlap, to bring together the two wave packets. And this is how bad we did it, how imprecise we did it. This is in position and this is in momentum. Whereas below you have the initial distribution of the wave packet, the initial wave packet. So this is the coherence length, and this is the, you might say, momentum coherence length. And so you look at the extent of the wave packet, initial wave packet, and you look at the momentum distribution, and you have to do much better than that if you want to get a good coherence. Yeah. So for example, if you take a trap of 100 kilohertz and you take a mass of 10 to the 7 atoms, you find that your extent, your wave packet or your ground state size is only 0.1 nanometer. So your precision has to be better than that. Otherwise, this equation kills you. And so today, in the atomic Stern-Gerlach interferometer that we realized, we could only prove a precision of 100 nanometer. So if we take that 100 nanometer that we have realized so far, and this number here, it's at least 3 orders of magnitude that we have to improve in experimental precision, in the active recombination that I talked about before. And we have thoughts on how to do that. Yeah, it's not that great of a number, but still there are 3 orders of magnitude that have to be done if we can cool to the ground state. And this is, of course, another if. Yes. So we have to talk about cooling. So, of course, there's center of mass cooling, there's rotation cooling, and there's cooling of the internal degrees of freedom. All these are important. I won't have time, I think, to really delve, to go deep into each of them, but let me just give very brief count. So center of mass cooling, of course, people have been using a lot, people in the business have been using a lot of optical and electrical and magnetic feedback loops. And actually, Brian Durso has recently told me that they already went below the 1 millikelvin with their feedback loops. And of course, Marcus has this recent paper about going to the ground state without a cavity, which I think is a wonderful, wonderful idea. And people have been working on optomechanical systems with a red sideband. So Hetet has been doing it with red sideband in microwave. Kippenberg has been doing it. Different groups have been doing it, and it works well. So I think that that could also work on the nanodiamond. Of course, you have to have resolved states, but the microwave is resolved. And you also have more exotic ideas. For example, I want to show you an exotic idea that I like very much, and that is sympathetic cooling. Now, how can you do sympathetic cooling in nanodiamond? So charge it. So let us charge the nanodiamond. I want to charge it anyway because I want to trap it in a Paul trap, which is the best trap. I mean, people have been doing diamagnetic trapping, and people can even do magnetic trapping with the gradients of the atom chip, but the Paul trap seems the strongest and the easiest.
Okay,
So,
Ron, 3 minutes.
3 minutes, wow.
Yes.
It's much shorter than what I thought. Okay, so I'll go very quickly. We simulated this sympathetic cooling, and this is, by the way, not our invention. This is now being done in GBAR at CERN to cool anti-hydrogen atoms, anti-hydrogen plus ions with laser-cooled atoms. So this is one example. I talked about the Paul trap. I'm not going to say more about that. Let me just say that we're already fabricating chips for this kind of sympathetic cooling for the GBAR experiment. These are now being tested in the lab of Ferdinand Schmidt-Kaller. These are the ions trapped in these chips that we fabricated. You have here a double chip, and we planned the interferometer to be inside the gap, 2 millimeter gap in this double chip. You have to minimize the phase. I wanted to tell you about the phase, but you'll have to ask me about it. The phase is huge. You have to play tricks to minimize the phase. If you have a phase of 10 to the 5 rads, you cannot do an interferometer. And we have interesting ways on how to zero the phase and just leave a small phase, which you are not suffering from jitters. And you have here beautiful trajectories that we simulated, where you can see that you can actually get very nice separations all the way from tens of nanometers to 1,000 nanometers. Here you see a gradient from a wire from an atom chip 1 micrometer away from the nanodiamond. And here you see coil, kind of the state of the art in coils in gradients for 2 orders of magnitude more mass. And rotation, I will not have time to talk about it, but we already are doing experiments about rotation. Here, experiment about the diabaticity of the NV center. Very interesting results. This is unpublished, but the PhD thesis is online. And rotation also makes us look at the uncertainty principle for rotation. This is something really beautiful in my eyes. And this uncertainty principle of the ground state of rotation puts limits on the best, the smallest fluctuation of the force, the Stern-Gerlach force that we can suffer. And all this has to be put in at the end of the day. And of course, finally, we have to measure. We have a unique signal that we saw from our atomic Stern-Gerlach interferometer, which is the T-cubed signal. We're very happy with this signal because it's unique, and that means that we could filter all kinds of fake signals by searching for this signal. And I will end by saying that at the end, you need to really design a crazy chip. So if you want the gradients to come from 1 micron away, so let's say you want the nanodiamond to be here and a current carrying wire to be here, you need many layers. You need a layer for the nanodiamond source. This is nanodiamond source. You need a layer of the 2 ion trap that I showed you from 2 sides. 2 ion chips with a 2 millimeter gap between them. I showed you that we already trapped ions in the lab of Ferdinand Schmidt-Kaller in this gap. So you start with the cooling here and the trapping and the Paul trap and the cooling. You take it up with this Paul trap to very close to the current carrying wire. You have to neutralize it. The minute you neutralize it, it starts to fall automatically from the Paul trap. Then the experiment actually, the interferometer actually start. And you need here also a layer for the polarized microwave antenna. I did not talk at all about the all kinds of microwave radiation that you need, but you need to control also the polarization. And so it's quite a crazy kind of multi-layer, multifunctional chip that we will have to fabricate for this business. Let me conclude. Clearly it's a hard experiment. Numerous cutting edge technologies will have to be developed, not by us, not only by us, but also by other groups. I mentioned some of these groups before. But at the end of the day, looking at the numbers, I feel that numbers that we are simulating, but also that other groups are producing, it seems feasible. Going back to the historical note I had before about the 100 years of Stern-Gerlach, it seems the Stern-Gerlach effect is far from completing its historical role. And for me, it's really a nice statement to make. And let me also say that if you're interested in all our Stern-Gerlach experiments in the past decade, there's a nice chapter that has now been written in a book in honor of Otto Stern. And thanks to Mark Kyle for writing this chapter. And I end by thanking the people who actually did the work. One of them you see here is Yair, who is still officially with MIT with Ketterle, and others have gone to different places, and now O is taking over the experiment. And of course, thanks to the many theoreticians that came to us with all kinds of ideas and calculation, and it was really a great help. Thank you very much for your attention.
Thank you for a nice talk. I should mention I never got a flight.
You never got a flight?
I never got a flight.
Well, you should have asked. I'm afraid to suggest, you know.
Okay, so questions. Anupam, please.
Thanks, Ron. As always, fantastic talk, very enthusiastic talk. And it shows that extraordinary physics requires extraordinary courage and extraordinary experiment, no doubt about it. So just one question I have, that I want to get rid of diamond. I want something different from diamond. What's your opinion? I don't think diamond is the future. Maybe we have to think something beyond diamond.
Yeah. Well, people are looking at all kinds of materials. There are many things in diamond that we don't like, especially the rather short coherence times. So people are looking at other systems, not us. We are trying to stick to the NV diamond, but people are looking at silicon carbide and other systems. As far as I know, I've not seen anything yet that is comparable to what the NV center in the diamond can do. But maybe it will come. So right now, I'm just judging by numbers. Right now, as far as I know, the NV center in the diamond is the best.
Thanks.
By the way, the diamond has another big problem. And that is the diamagnetic character, and some of that horrible phase that I said that we must zero. Even if we play a lot of tricks about the Stern-Gerlach phase, and that's the T-cubed phase that you saw the equation, you still get horrible phases. You still get horrible phases from the diamagnetic interaction with the magnetic field. And what I didn't show you is a little trick we're playing here. And that is that these green lines here, these green lines is actually we're the gradient in a quadrupole field. So it's a quadrupole field, and this shows you the position of the zero of the quadrupole field. So by moving actually all through the experiment, the zero of the position of the position of the zero of the quadrupole field, we are lessening the interaction, the diamagnetic interaction, because we're close to the zero. And the diamagnetic interaction goes like B times B prime. And so if B becomes smaller, you manage to really take the diamagnetic interaction down. That's a very important trick. which we already played, by the way, for a different reason. We played this trick in the atomic Stern-Gerlach interferometer. We played it to get the noise down. We played this trick and it worked wonderfully. We're also thinking, I didn't mention it, about reducing the diamagnetism by coating. On the chip, we can make very, very thin coating of opposite sign susceptibility materials. And we think we can get to within 1% of zeroing the diamagnetic interaction. And you see here that we mentioned here the number 1%. So some of these graphs are with full diamagnetic, like here, full diamagnetic force. And in some of these graphs, we look at what going down to 1% diamagnetic force would look like.
Thanks.
Okay. Any more questions? I see that Andrew has a question.
Yeah, hi, Ron. Very nice talk. So just a question about the Paul trap. Are you concerned at all about any backgrounds that the Paul trap might impact on the sequence once you remove the charge and then perform the rest of the experiment?
We actually copied our lack of worry from GBAR. The GBAR collaboration I mentioned before, because what they're doing is actually doing all this sympathetic cooling and then neutralizing their anti-hydrogen ion, and then it drops, and then they're going to do a very sensitive gravity experiment with their anti-hydrogen. And they, I think, are even more sensitive than us to what the electric fields might do. But in any case, I hope we can shut down the Paul trap quickly enough. Once we see that the nanodiamond has started to fall, we will have some time. So once it starts to fall, we can shut down the Paul trap and only then apply, of course, everything has to be very fast, then apply the current in the wire. By the way, this has to be a high current density wire. We're looking at special materials like copper embedded with CNT. CNTs, which is now holds the world record for material with high current density. Something like 10 to the 9 amp per centimeter square. The short answer is no, we're not worried. But you know, you should always be worried. By the way, since you mentioned the Paul trap, I should say that it has a very nice feature which we like, and that is that the charged nanodiamond is not only held by the Paul trap, but it's also aligned to the axis of the Paul trap because of the distribution of charges. So we actually get for free a nice alignment of the nanodiamond, and we can even rotate the axis of the Paul trap to have it go to the direction of our quantization, magnetic quantization axis. So the Paul trap actually has many advantages. Right now, I hope there are not too many disadvantages with the Paul trap.
Thanks.
So we're already past the time. So let's say we are starting the discussion and